Hello, I'm Katie Steckles.
And I'm Peter Rowlett. Hi Katie, what's today's mathematical object?
Today's object is a 100 square, which is a device which, if you haven't seen one before, I'd be very surprised, but it is a grid of 10 squares by 10 squares containing the numbers up to 100. I guess, in rows. And this is something that if you've been to primary school, which many people have, you may have seen one before. But this is kind of a cool thing. And we've brought along a special guest to talk about this. Susan, hello.
Hello. Yes, I am a maths teacher, but sort of secondary maths teacher. But I've worked in primary schools, and the little work I've done in primary schools has opened my eyes to some of the really rich maths that quite simple or basic things can bring, and the 100 square is one of those things. So I just think they're brilliant. The reason I think they're brilliant is because I was working in this primary school and I was given an activity to do with some kids, and it was just they were given 100 square to fill in, and then they were given a number, and they had like a square above the number, square to the bottom of it, square to the left and square to the right, and they had to fill it in like it was in 100 square. And it was like, so say it was 63, the number above would be 53, the number below would be 73, the number to the right or left is 62, and then 64. And then it was like they had to do this for a series of numbers, some numbers bigger than 100, and then understanding the idea of like place value, and also the relationship between numbers, that if you were to go up, the square above would be you're taking away 10. So what's happening to your tens column? The square below would be like adding 1 to the tens column, and then to going back 1 would be taking away from the units or the ones column, and going forward 1 would be adding 1 to the units or the ones column. And it was just this idea that this is a universal thing with our kind of counting numbers, or our integers even. So you could even take it to sort of negative numbers. And as soon as that was like, I saw that, I was like, oh my God, this is so rich. This is so interesting. And like, what can you do with that? So I just think it's great.
Yeah, I really like that, because I've seen that working with kind of primary school children, and just the amazement that they have that there is this really nice pattern in there. Like, you notionally know that you've put the numbers in rows and that there's 10 numbers in each row, but then when you actually look at it and you think, what does it mean to move upwards and downwards in this square? Actually, it has a very clearly defined meaning, and it kind of tells you something about the way that decimal numbers are structured. So it's kind of cool.
Yeah, so a couple of weeks ago I did this with my son, so he's 5, and I printed out 100 squares for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I had him colour the multiples of each one. So he coloured in all the multiples of 2, and after a couple of rows he worked out that it was just stripes down the page, and then he just coloured in the whole stripe. And a lot of them were, as you say, they were sort of like 9 is down and across 1, or 11 is down and across 1 the other way, and things like that. And so he was kind of working out those patterns as he went along, and I don't know, it's sort of giving him this sense of what's happening as you move from one row to another, and I quite like that. And like 8 is like a move a knight makes in chess, so he was quite liking those sorts of things. Cool. And things like that. Yeah.
Well, this is the thing. That's one of the things that the exploration of 100 square. I think for me as a secondary school teacher, there's so many issues with regards to students understanding relationships of numbers. And so, like they don't necessarily, if you were to say, oh, take away that 9, they wouldn't understand that that's same as taking away kind of 10 and adding 1 type thing. And it's that idea that you can visually see that on a 100 grid, and you can play around with it, which is just really powerful. And then you can bring in things like times tables or multiples, and then the visual connection. So it's not just about the numbers, it's kind of what they visually represent as well, which can kind of help with people then, like jumping forwards to maybe more complex numbers, which could be, thinking about thousands or millions, or decimals, where it's like, it's the same relationship really, but you've just scaled it down by 10 or 100 or 1,000. And that's our number system, which is just kind of like, it's about playfulness, which I think for me, it's been a real like eye-opener to just sit with this thing that's quite basic and then just see where it takes you,
Yeah, I think the traditional thing to visualise numbers is a number line, and that's fine because it gives you sort of less than and greater than, and it gives you a perception of how big numbers are. But at the same time, it doesn't like, because we always work in decimal, it doesn't necessarily give you a handle on that, but this is kind of a different way to visualize the way that numbers relate to each other, I guess. And I think that's really nice, because like making something visual can help people quite a lot to kind of get their head around it, especially if you've always thought of it as being quite an abstract thing. It's quite a nice concrete representation.
Yeah, no, it's and that's the thing. That's so what you said, Peter, about like getting your child to sort of colouring for the times tables. Like, that's something that I've tried with, say, like working with sort of like lower sets or lower retaining sets of students who generally find maths a bit more challenging, but they still have the capacity for it. But I think we just don't necessarily give them enough time. And it's things like, I have no qualms about giving a year 9 group a 100 grid and asking them to colour in the multiples of 3. And it's kind of, because it's, for some of them, they're just relieved that they're not having to think about what the multiples of 3 are. But also, most of them can count up. They just add 3 each time. And when they see a pattern, there's suddenly a light bulb of, oh, wow, there's a pattern. Also, they suddenly realise as well that times tables go beyond 12 or 10. They see that it could go further. And it's like, you could speak to them about, like, if you were to extend it down, what do you think the pattern would look like? And then you can then play around with the whole idea of what the numbers are. So then, maybe play around with the digits and like, can they notice anything there without it being a stressful experience? And some of them will notice things which will help them hopefully remember what multiples of 3 are, up to the multiples of 3 to 12 or whatever. But and understanding that it goes beyond.
Well, yeah, and I remember, so my son and I got to talking about like multiples of 3. Once you get beyond 30, it's the same pattern again. And things like that. That's sort of quite nice, isn't it? And I was trying to get him to, because he coloured all these in and he quite enjoyed choosing the different colours and all that. There's this sort of fun creativity about it. But also then trying to think about which numbers are coloured in different grids, So like 6 is coloured in several grids and things like that. And that was quite nice, trying to get him to think about that connection.
I've been asked a couple of times in my capacity as a maths person, do you think it's worth kids learning times tables off by heart and things like that? And it's, I'm not strictly a teacher. I don't know exactly what's the best thing to recommend here. But what I would always say is, by all means, memorise some stuff. But if you understand the patterns, if you can see why the times tables are the way they are, that will help you more. Because in the future, instead of having to, recite a poem about numbers, which is essentially what memorising things are, you can actually kind of have a sense of why those numbers are multiples of whatever, and you can spot patterns in them, like, the sum of the digits of a multiple of 3 is always a multiple of 3 and stuff like that. And having those kind of insights is more useful to you going forward. So that's always the answer I give.
100%, because that's the thing. I think, yes, on some level it's nice, it's useful for kids, for people to just know some facts. Do you want to be having to work out 3 lots of 4 by counting up or whatever? If you know it's 12, that's just a load off your mind. But it's it's more than that, isn't it? You kind of want to understand that is 3 lots of 4 things. You also want to know what that looks like as a calculation. You also want to know that then to get 5 lots, you're just adding on another 5 lots of 4. You're adding on 4. 5 lots of 3. You're adding on 3. That thing. And the grids is just quite nice because you can take the times table thing is such a hurdle for so many people, I think, in the classroom, because so many people think you should just know them. That's a given. And if you don't know them, you feel really stupid if you don't know them. But actually, for those who did know them, they probably learnt them when they were little and it was playful and they just remember it and didn't remember how they remember it. But what's great with a 100 grid is the fact that you can take away the whole thing, you need to just know this, you can work it out and can you notice something which will hopefully help you remember it. And also puts a context of it's more than just the ones that everyone remembers. It goes on to infinity, which is kind of mind-blowingly big, and that's a much better understanding, because you then think, well, if 3 times 4 is 12, then what is 3 times 40? What is 40 times 3 or whatever? And it's trying to get them to understand that relationship is kind of still there in a bigger sense.
Yeah, because you can start at any point and you can it's still the same thing, that you're still going down a row and across or whatever it is that you at any point in the numbers. Because I mean, I was always terrible at... I just don't have a very good memory. I was always terrible at things that needed memory, like, classification of things in particle physics or biology or whatever. I was just dreadful at all that. And, so this was one of those. Times tables was one of those. And in primary school, it was a big problem because you'd often get sort of told off for not being able to remember, what is 6 times 7 or something like that. And I tried really, really hard, and I forced myself to learn the squares. And I could already do the 2s and the 5s and the 10s. And between that, I was always near enough to the number that I needed that I could work it out. So if you asked me 6 times 7, I would think, 7 squared is 49, then I take 7 off. But I could not remember that it was 42. And I still like that. But I think I could do that quickly enough that the teacher thought that I just remembered it, and then they were happy, and we could move on, and I could get on with my life. But I think that probably did me a lot of good, right? Because
but your answer, that your strategy is like, I'd say as a teacher, that makes me go, oh my God, he understands. Do you know what I mean? As opposed to just knowing that 6 times 7 is 42 or whatever, you're like, oh no, he has a complete strategy to work this out. So you then again be able to work out maybe what like 70 times 6 is, because you're thinking more about how the numbers are related.
Yeah. But I definitely thought I found a clever way around this memorising. I couldn't remember how to spell words, and I couldn't remember times tables, but I'd found a clever trick for one of them.
Yeah. What was your degree?
Maths.
Well, this is it. This is kind of a massive proof that, like, yes, not times tables, I think it's useful to, like, know them. But I think understanding them is so much more important. And you didn't memorise them. You understood what the maths was, and that you were able to do a degree plus in it. Do you know what I mean? So that's, the power of it.
Yeah, I remember in our primary school we had a tree on the wall. It was like one of the big wall displays. It was a big tree and it had 12 branches. And if you could memorise that times table, if you'd go up to the teacher and recite the times table, and I think they asked you a few random ones to make sure you weren't just memorising a pattern, so that you actually understood what you'd memorised, then you got a leaf with your name on it on that branch of the tree. So it was this big thing, like, can you fill up all the branches with your own name? And like, once you'd done 1 to 12 in all of them, I was like, great, I don't think I'll ever need a number bigger than 144. That's probably the biggest number I'll ever need. I'm all done now. That's good. And I don't remember it ever being about anything other than just, can you do this task, can you repeat these numbers back to someone? And it was later that you kind of make the connection between that and patterns and numbers and things like that. But yeah, it's such a weird pressure to kind of memorize a thing, because it is useful, it's useful to have those things as a shortcut, as a quick answer. And I know that if you get later on and you don't have the immediate ability to come up with an answer to a simple calculation like that, it can really slow you down and it can really affect you later on. But is memorizing it the best way to do that, or is it better to do something more?
Yeah, well, this is why, for me, so this is what it's been really weird. Like, I enjoyed maths at school. I was always quite good at it, I guess, but I didn't really think of myself as that way. But then went to do the degree in it, I found it really challenging, and it kind of lost a bit of the love. And it's been since teaching that I've gone, oh, okay, like loads of things I kind of just got. You kind of go into depth and go, that's amazing. Like, I didn't know, I didn't understand where that came from. And so, like, going to primary school was even more of a mind-blowing thing, where, like, doing the work with the 100 square was, like, really interesting, where you think, okay, so the times table thing, you're like, okay, well, like, colour in the 3 times table. Now colour in the 6 times table. Now colour in the 9 times table. And what do you notice? All of those numbers are in each other. You know what I mean? And it's because they're 6 and 9 are multiples of 3. And you go, oh, wow. So then you do the same with the 2. The 2 times table, the 4 times table, the 8 times table. What do you notice? They're all in those, like, as you say, the lines that you said that your child will have noticed, Peter. They're all in there. Can you notice something about those? And when you start to think of the 5 and the 10 times table, they again are the lines. And you kind of think, right, if you know that, suddenly you can start playing around with the relationships and the patterns that are there. And the relationships are the key, I think. Because if you sort of know how they're related and things like prime numbers and all that stuff, you're like, suddenly this wealth of, like, interest builds. And I think it's the interest that's kind of that we should be really trying to, encourage in kids. It's like the whole idea of, like, wonder and stuff. It's like, wow, this is happening. Why is this happening? Or how does this help me later on? And that's what I just love, the fact that just by a few colouring pencils, you're like, this whole area of math is suddenly like a lot kind of bigger and broader.
Yeah, I mean, like,
you know?
prime numbers feels like a much higher concept than kind of primary school level. But you know, if you colour in all the multiples of everything, it's the sieve of Eratosthenes, right? They drop out, and the things that you don't colour in somehow have this magical property that they're, you know, they're these numbers that have escaped the colouring process. That these are somehow special.
Yeah. So there's this game called Prime Climb, which has this. Have you seen this? And it has
amazing.
So each number is a little disc, and the prime numbers are given a colour, and then the other numbers are given sections, which are the primes that are its factors. And that's really nice. So we've done that you can get it as a colouring in sheet. So we've done that, my son and I, where he'll colour each of the multiples of 2 with one of their segments to be a 2 colour and all that. And that, I mean, I think it was a bit advanced for him, but he sort of enjoyed it. And again, it's the choosing of colours and the playing around. And he really always points out the 11s in that, because he coloured them in like a particularly dark colour or something, and he can really see that line going.
I noticed. So the Prime Climb, I've not played the game, but I've seen the sheet, the kind of the 100 square that has like the factor of it. It's just amazing. Is it Dan Finkel, I think, was the guy who designed it? He did like a TED talk, and like, because when he does it, I think in the TED talk, which I'd recommend people watching, it's kind of about this whole idea of like wonder and what do you notice. And I think like if you have a knowledge of like number and primes and stuff, you're like, oh wait a minute, I do notice something. And then what's great is in this one kind of like sheet, you see all the prime factors, all the numbers from like 1 to 100, and you're like, okay, because there's loads of numbers that if you're asked like, oh, you know, divide 97 by 3 or whatever, you're like, oh god, can I do that? Is that a thing? And like suddenly by just seeing like a little thing, you're like, oh, actually this is feasible, this isn't feasible. Or like, you know, what numbers have prime factors that you don't, what numbers have got 17 as a prime factor, because a lot of them you don't know. Like, you know, if they pop up in a question in math, you're a bit like, oh, without a calculator, you have to really think about that, and you might have to do some short division. But in this, it just sort of shows you like loads of like, it's just a really wonderful visual representation of the 100 square, where you're thinking about like factors as well. And it's like, as you say, it's just really powerful, I think.
Yeah, and a fun programming challenge, because I started, if anyone uses LaTeX, the typesetting, I started using Lua Tech, which is a sort of, it has the Lua programming language on top of it, and just as an exercise, because I find I learn a programming language better if I've got a use for it. So I just programmed this, and it is basically, as you say, it's the prime number sieve, except that you also keep track of the colours, and then there's a bit of trigonometry in there to work out how many factors a number has determines how many sections you need this circle to divide up into. For actually drawing the thing. So it's quite a nice little exercise, really.
That's the thing. This is the thing. It can go it's so basic, but then it can go so complex, which is just, you know, really wonderful. To kind of join the dots. I think as a secondary school teacher who understands a bit of what you're saying, it's like, oh god, I never thought about that before going to primary school.
Yeah, well, I remember at uni it was like this point where we were talking about number theory and about prime factors of things, and it's called the fundamental theorem of arithmetic, and it was this moment of like, oh wow, it's really important. that sounds really serious, like that this numbers can be broken down into prime factors, and like, actually, yes, it really is that important, because that's how you build numbers, and that kind of system of, you know, building things up out of prime, you know, components is echoed in so many other types of maths as well. You know, you get shape versions of that, and, you know, topology things and all sorts, where you've got these sort of prime units of stuff that you can combine, and it's really nice and satisfying as well, like to sort of see things from that way. And yeah, kind of having the colours, like I've seen people do really nice art pieces where it's, you know, the colours of the prime factors of things, and there's something really pleasing about it visually as well.
Yeah, I, as I say, I wish I'd like to spend, and I'm hoping to, like, when next year when I'm back in sort of school, I'm hoping to like actually make time to just play around with this, because especially with students who find who are in sort of the lower attaining sets, just for them to understand that they don't have to remember, but it'd be good for them to notice, and there's fun ways of noticing and seeing relationships, and yeah, like, and also for me as a teacher, like what you were talking about, the idea of kind of where it links to geometry. I don't have much of a knowledge of that, and I think that's super interesting. Like, it's kind of, we deliver this stuff and loads of kids get into the idea of procedures like finding prime factors, like using a factor tree, but then relating it to actual numbers that are related to each other. That isn't done very often, I don't think. Yeah, it's not kind of, it's like here's a number, what are the prime factors, plug it in. You can then maybe find the highest common factor between this and this number, or the lowest common multiple between this and this number. Next, do you know what I mean? And that's a bit of a shame that it's not linked.
Here it's because the prime climb colouring sheet just comes with, if a number's got 4 factors, it's divided into 4. So you've got 4 areas to colour in. But of course, drawing it from scratch, you don't know that. No. So in my programme, I was having to count how many factors are there, and then what, basically drawing an arc, and then drawing a line, and then drawing another arc, and drawing another arc. So you had to work out the geometry of how many. It wasn't a hard bit of maths, but it was just quite nice that fell out of it as well. But
where's your programme? What's the situation with that?
It's on GitHub. I can put a link to it, and I can send you a link. And
that'd be great.
I'll put a link in the show notes.
Yeah, that'd be great.
So you wanted to talk about 99?
Yeah. Yes. So with the little bit of sort of play research that I've been kind of doing, looking at the 100 square. So obviously I'm a bit fascinated by it, but also I was like, okay, what's actually been said about it? And found this really great kind of article by, it was Midge Pasternak. Fantastic name, and it's for the ATM, and it's effectively he's arguing that a better setup of the 100 grid, which we're used to 1 to 100, and he's arguing that, I think it's he, he's arguing that it's 0 to 99 is a much better layout, because one acknowledges the importance of 0, which is probably like the most, has no value, but the most valuable digit, really, because it kind of makes our number system work. And if you start with 0, all of the multiples of 10 are underneath it. So there's obviously, it looks nicer. And then with that, you then also have this whole idea of, there's more symmetry in the grid. And it was like, the article just, again, blew my mind. It's something I'd never ever thought about, and just the whole idea that we talked about the power of like multiples and times tables, but this was about kind of place value and the importance of like having the 0, the relationship there, and then thinking about where you have the vertical line of symmetry and the horizontal line of symmetry. And so what happens with the 0 to 99 is your vertical line of symmetry goes before the 5. So it'd be 0, 1, 2, 3, 4, and then after that line it'd be 5, 6, 7, 8, 9. So that'd be for all of your grids, yeah? And what that helps with is the whole idea of rounding to the nearest 10. And we all know, we like, this is what we sort of say, is if your number ends with 5, 6, 7, 8, or 9, you round up to the next 10. If it ends with 0, 1, 2, or 1, 2, 3, 4, it rounds down to the previous 10. The problem with the 1 to 100 grid is if you put that vertical line of symmetry in, it's between 4 and 5. So that makes that much harder to kind of understand, which is a shame because but it's also, if you have the look at the horizontal line of symmetry, the one that goes across, and we were to go the 0, 1, 0, 10, 20, 30, 40, and the horizontal line would come in there and it would end at 49. Again, underneath that, 50 to 99, you'd round to 100, and then 0 to 49, you'd round to 0. So it's this whole idea of it's a great way of sort of showing the power of rounding and where those lines are. So again, that was like, blew my tiny mind.
And that feels, it's sort of related to this. Well, it's quite nice if each row has everything that's a single digit, and then everything beginning with a 1, everything beginning with a 2. Mm. It feels like it's a bit related to this problem people have with when does a century start and things like this. That, isn't it? Because there's that sort of edge bit, and is it in the next category or the previous category? And people really struggle with that sort of thing.
And it also ends on, like it's that whole idea. I think a lot of people find the whole idea of the next digit. If you're adding on 1 to 9, what happens? And it kind of needs to fall off to the next one. Because I think a lot of, especially when you get kids, like what comes after 0.9, some of them will go 0.1 because they're not understanding to go down to move on to the next place value. And so with this, you're going on to the next row. So you're going on to the next place value, or you're adding 1 onto the next 10 or whatever. And so with that, it just makes it a lot tidier. And again, that was really like mind blowing for me. And then it kind of was looking at the whole idea with that as well of, if you extend it down the way, you're then thinking about that's 10. So 100 would be 10 lots of 10. And then you could kind of continue it further down in a kind of much smoother way, as opposed to ending on 10 lots of 10 at the end. You'd be starting with 10 lots of 10. That makes sense. So it's a bit tidier as a beginning. So that was kind of, I thought, really great. And then they talked as well about the whole idea, of when you then have 0 to 99 in your grid, the diagonal from 0 to 99, all those numbers are the 11 times table. And the diagonal from 9 to 90 is the 9 times table, which doesn't work if it's 1 to 100. But that's amazing, because obviously 9 and 11 are related to 10, and it's nice to see what's kind of going on there. So it's just kind of the two diagonals are the 9 and the 11 times table, which I was like, again, this is amazing. Yeah.
Yeah, it kind of feels more intuitive somehow to have, because going up to the next number of tens is sort of like resetting a counter, and to have that at the start of the next row is much nicer. I think also my the typesetting head on, if you've got all 2-digit numbers and then 100 at the end, you have to have the 100 in a slightly smaller font for it to fit in the same size box. With the 0 to 99 square, that's not an issue anymore.
I think that's not a small thing, actually. Formatting is quite a big deal. I think what else, kind of the whole idea of, they talked about sort of the whole idea of subtracting as well, and how much like using the 0 to 99 grid is much more intuitive, because everything, I suppose, is like neatly under each other, if you know what I mean. So again, you've got all the things that end with like 9 on the same row, obviously at the same column. But I think how it works is, if we started, say, at 16, and I was to take away 10, you just go back, and that works. It'd take you to 6, which would work the same for a 1 to 100 or a 0 to 99. So say if we had 23, take away 10 would take you to 13. And then if you wanted to take off another one, 11, that would take you to 12, and another one would take you to 11. And then, because the whole point is, it's trying to get you back to 0, and the getting back to 0 is quite an important, quite a powerful thing when it comes to subtraction. And the problem is with a 1 to 100 grid, it takes you back to ones as opposed to 0. So the whole concept of coming back to 0 with the 0 to 99 is just so much better, because that is like our canceller, and that makes everything again much easier to like move around the grid.
Yeah, I feel like, so with subtracting, because quite often practically the kind of questions you're going to be doing are like, what's the change from a £10 note or whatever. So getting back to zeros is often the kind of the goal with that kind of thing. And yeah, it must be much easier to sort of see that happening with the zeros down the left hand side. And
also just it's validating that 0 is, I mean, it's not a number, it is a number, and it's a place to get to. So what the problem with the 1 to 100 is the fact that before 1 there isn't anything, but we all know there is. And actually beyond 0 there's negative numbers which we can totally go into, and now you can, with the 0, extend down the way again, just almost like a mirror image of the grid in negatives, and suddenly you've got your integers, and that is incredibly valid and very powerful and incredibly useful, especially as a secondary school teacher where kids have real issues with negative numbers. But with the 0 to 99, you can bring it in without too much of a problem, because you know there's a 0. So what happens when you've got nothing? Less than nothing is the next phase, which again is really, I think, potentially quite powerful.
Sorry, I'm now thinking about a minus 50 to plus 50 grid or something.
Yeah, but this is it. I think it's that thing of like understanding, like that, you know, if you go the same way, if you're thinking about just space, if you go up a certain amount, but then go down the same amount, takes to 0. And that's exactly, you know, that's adding and subtracting with regards to negative numbers. This whole idea of like, you know, add on 50, take off 50, you get nothing. And that's like useful, but the 1 to 100 grid, the 1 to 100 square doesn't incorporate that. So then you have to, as a cognitive thing for kids, or people, is they have to rethink, that nothing matters. And it does, we all know it matters. Like, if you haven't got anything, if someone wants to take away from that, you have less than what you had before and you're into negative, which is a hard concept to understand if you've never experienced it or you haven't been, exposed to it. And so when you're exposed to it a bit later, it's quite hard to just add on a new idea at the end of something that's been quite concrete into your head. But if you're introduced to it early, this whole idea of zero, of nothing is a really power thing or zero is a really powerful thing to play around with. And there are also numbers between 0 and 1, which you can also talk about.
Yeah, I'm liking the idea of a 0 to 1 square that's got, 0.01, 0.02 all the way up the grid, yeah.
Yeah, it can be scaled up and down. That's the magic. You can have a 0.001 if you wanted. Or more, or less.
Yeah.
Cool. So I've got a website called dothemathsthing.com because I like to do maths. And I'm also a co-host of a podcast called The Maths Appeal Podcast with the wonderful Bobby Seagull. You might know him from University Challenge fame. And we're also doing these puzzles. So we're going to be doing video puzzles as Maths Appeal on YouTube. So watch this space. And you can find me on Twitter at Do The Maths Thing, and that's with an S because I'm in the UK. And also the Maths Appeal podcast is at Maths Appeal, again with an S. And obviously we'd love to we're really into people kind of communicating with us. So if you've got ideas for puzzles, or when we give puzzles, we really love people to answer them. We're into sharing solutions. So we're kind of into that communication of mathematics. So definitely look us up.
Cool. Fantastic. We are also on Twitter. I am at Stex.
I'm at Peter Rollett. The podcast itself is at Maths Objects.
And both Peter and I blog at a website called The Aperiodical, which is aperiodical.com, which is also where you can find more episodes of this podcast.
And if you'd like to get in touch and tell us how you've been using 100 square in your everyday mathematics, then you can email us objects@aperiodical.com.
Lovely. It's been a real pleasure.
Yeah, thank you. That was really good. That was good fun.
Thanks very much.
Yeah.
Enjoy your 100 square.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.